14.2 and 14.4 are similar because they're both involving light. And there are certain things in each of them that I want to discuss. So you're going to see the notes are together for these two sections. So 14.2 is about mirrors and just reflection, and 14.4 is about colors and the idea of polarization. So we're going to go through some of the main ideas here, and then we're going to spend about 10 minutes at the end just watching like 2 short videos about light and how it's commonly confused as far as its primary colors with that of paint or art. So artists in the room or painters in the room, what do we know? For painting, what are the 3 primary colors that you learn? For painting, what are the 3 primary? What do you got?
The primary color is red, yellow, blue.
Red, yellow, and blue. Is that correct for art? Yeah, so for light, as far as transmitted light, we're going to look at red, green, and blue as our primary colors. But again, the colors for art are pigment colors, right? They're called pigment colors, really. For light, we're talking about light colors, or colors of wavelengths. So it's going to seem like you're going to be like, wait, how does that work? Those lights don't make, those 2 colors combined don't make sense. But we'll talk about how the wavelengths interact with one another. Remember we talked about constructive and destructive interference? That's what you're going to see happening today. Okay, you're going to see where there's a filter, and we'll look at the video, where if there's a red filter, only red light propagates through. But then if you put a red filter up and then a green filter afterward, you're going to get no light, actually, which sounds weird. You'd think it would be a combination of the 2. But because only thing that passes through a red filter is red light. And then if red light is going through a green filter, the only thing that would go through a green filter would be green. But in red light, there is no green. So nothing ends up going through, so you get no color whatsoever. So it's just a little bit different than what you've seen in art. So just try and keep the 2 things separate for now. There's some overlap in the ideas, and you'll see that a little bit later, where if you combine some of the colors in an area, you get white light. Okay, we'll talk about that, how that works.
Why wouldn't there be other colors?
So when you see red, what you're seeing is the reflection of that wavelength only. So if you put a filter like red cellophane and you were to shine light through it, only red light would come through because it only transmits red. But then if you put another green filter after that, a green filter only transmits green, right? But only red is coming through. So nothing's going to go through. So if you put them back to back, you'll get no color afterwards.
Why is it like any other colors? Like why not blue?
Other colors too, yeah. Those are examples. Those are just examples. So our 5 main objectives are going to be to distinguish between 2 types of surfaces, specular and diffuse. Where have you heard the term specular or something that sounds like specular? Glasses, right? Like your spectacles or your glasses. We're going to talk about the law of reflection, which is probably the easiest law you'll ever learn. Okay, it really is. We're going to look at, again, additive colors for light, how pigments are affected, and then talk about polarization. So first, reflection. By definition, it's when an EM wave is redirected from a surface. When an EM wave is redirected from a surface. You think about reflection, you think about mirrors, right? Because what you're seeing is those light waves being reflected back at you. Okay, that's why you say, what is your reflection? It's what you see aiming back towards you. When it comes to EM waves, though, can somebody think of an application outside of visible light? Of EM waves, think about all the EM waves. We talked about radio waves, ultraviolet waves, microwaves, gamma rays, X-rays, infrared rays. Anything outside of outside of visible light that you can think of that has to do with reflection.
Like sonar when it comes down and comes back up.
What was the first word you said?
Sonar.
Sonar, yeah. So any sort of wave that's sent from like maybe a source that gets reflected back up. Now, sonar is difficult to use for this example because that's sound waves. Those aren't EM waves. But the idea is the same. The idea of a wave bouncing back, okay?
X-rays?
How do X-rays work?
I don't know exactly, but it kind of reminds me of bouncing back up. In case it sends something to you and returns a picture of your insides.
Okay. The only thing about X-rays, though, is a lot of time it's what's transmitted through the surface, so based on the density, what waves are transmitted through. So I don't know if there's a lot of reflection going on there, but I understand.
I thought it was that the ones that reflect back, the other way around, not the ones that go through.
But they're not. They're being scattered. They're not necessarily being reflected. That's a little bit more. I'm talking about things that are actually like reflected off of a surface that you can clearly see, like an X-ray, based on the density. I'm pretty sure it's how it works. You can look up though. The waves that are transmitted through get printed on the screen versus the waves that aren't transmitted through. They're not necessarily reflected back to us. But they're stopped in some way. So they're not transmitted. But there's an example that I'm thinking of that's really obvious about EM waves that are reflected. Because the idea of sonar is analogous, but it's not an EM wave. What's an EM wave or an example of one? I couldn't hear. A mirror, yeah, but no visible light, I said. You're just naming waves now. I want an application, guys. But what application of it?
Surfboard.
Wait, what was the question again?
Surfboard.
Okay, that's a good one, and you could extend that if you go a little further. Remember when you put sunblock on in the summertime, and it says UV index 8 or UV level, whatever it is, SPF 30, SPF 45, right? Those are things that stop the UV rays, so they're going to, I guess, transmit them off your body. I wonder if it's reflected though evenly. The one I'm thinking of is a satellite dish. Think about how a satellite dish is shaped. What shape is a satellite dish usually?
Like a dish.
Like a dish, right? Okay, you got some sort of like a bowl. So imagine drawing this. Draw this in 3 dimensions now. Whoops. Let's draw something that's 3-dimensional. Okay, so here's like a cereal bowl. Okay, so it dips in. Now usually there's some sort of a antenna that comes out of here with some sort of a focal point on the satellite. Does that look good for a satellite, right? It's pretty good. All right. I know, thanks. So, I've been working on it. So what you don't always realize is that the contour or the shape of the satellite dish is what allows it to focus that EM wave on the focal point. So what happens is this. An EM wave comes in, right? Hits the dish and gets focused back to that center. Another EM wave comes in from another direction, comes in at a certain angle. And I'm not going to draw what it looks like in there, but it comes back out. And it hits the dish, or hits the focal point again. So it's hitting this wall maybe in here somewhere, right? Coming back like that. That's really what's happening. So the dish, the shape of it is a reflector. And that reflector concentrates or focuses all those waves on that focal point, or that receiver, or this transmitter here in the satellite dish. Okay? And you always see that little knob in the middle. That's what that is. So these waves are being reflected back toward there. And when you used to learn about parabolas in high school, you were taught with something called a directrix, and a focal length, and a focus. And now parabolas we teach with ax squared plus bx plus c, the standard form for a parabola. But when I was younger, we used to learn about these terms. They're not taught much, but the application that was the most widely used was a satellite dish, because it's a parabolic shape. Think about a parabola, right? Imagine taking a parabola like this, and a parabola like this, and a parabola like this. Eventually, if you put enough parabolas next to each other, you get like a bowl kind of shape. These are all parabolas lined up after each other. So that parabolic shape is what allows it to focus on that focal point. So this is a good application of reflection. Other examples of reflection, as many of you said already, a mirror, right? Visible light is reflected in a mirror because there's glass and there's some sort of metal or metallic surface that has a lot of luster. Okay, it can reflect light, it can shine. All right, here. If you've ever looked at two surfaces, okay, this desktop here would be considered to be most likely specular with some grooves on it. But imagine this desk surface in front of you before, 10 years of work were performed on it, or 10 years of students scratching, paper clips on it, or you're writing with your pen, or different things. You see all the markings on it. But imagine the surface really polished. That's what a specular surface is. When the light rays hit the surface, they come off at the exact same angle. We'll talk about that in a minute, but the rays are parallel here. See these rays coming off? Look at these 4 rays. They're all parallel here. But the diffuse surface, what do you notice about the rays that are coming off a diffuse surface, Nick? Yeah, what do they come off at? What kind of angles? Random or arbitrary angles. So we see this one reflects this way, this one goes off this way, etc., etc. So for a diffuse surface, the light waves are not bounced off at parallel angles. Okay, at parallel angles, they are scattered. So a mirror would be specular, right? A mirror, the light waves that get bounced off there. But maybe for example, when you're walking in the city, concrete does reflect some light off of it, but that surface would not be specular. That would be a great example of a diffuse surface. Okay? All right, this is the law of reflection. This is what I was saying before, why this is the easiest thing in the world. Just read it to yourself real quick. Okay, just read the law to yourself, and it's really just the simplest thing in the world. You can see it with the easy demo here of the light. So when a light wave hits the mirror, it comes off, and you take a look. These angles are what?
Parallel. The same.
The same. Congruent, not parallel. Thank you. Okay, so the angle of incidence is equal to the angle of reflection. Now, please make sure that you don't use theta r for reflection, because we're going to use that in the next section for refraction. Okay? So we're going to call the angle of incidence, which is the incoming ray. Okay, the angle of incidence is just theta. The angle of reflection is called theta prime. Theta prime. Prime just meaning afterward. Okay, it's like a little apostrophe. That's all that is. What is the angle being measured with respect to? What do you notice in this?
With respect to the normal.
The normal, or the vertical direction. In a lot of our examples this year, where have we measured angle? We've measured our angle theta between the horizontal and like that vector. It was usually this portion over here. But notice for these, it's with respect to the normal. The reason it's with respect to the normal is because of refraction, really. Eventually, we're going to take a look and say to ourselves, what happens if light goes through glass? It's actually bent at an angle. And we're going to look at how much it's bent with respect to the vertical, the normal. Because light that was coming in at 90 degrees would do what? On a surface like this, a mirror. If the light was coming straight down, it would go straight back up. So it would come back up vertically, right? So what we're trying to do is determine how much does that deviate from the normal reflection of coming straight back up. And when we look at light that goes through glass, if you take a flashlight and shine over glass, that light wave hits the glass, it gets bent actually. And we'll talk about that in chapter 15, but then it comes back out straight. But that bent angle, we're looking at how much it differs from where it was coming in at. So we're always going to measure angles with respect to the normal when it comes to light waves. Okay? Light waves on incident surfaces are going to always be reflected or measured with regards to the vertical. Across the room? It's just, sandpaper. You asked last time, remember? The test? Enjoy the sandpaper. All right. So the next thing I want to look at, so that was everything in section 14.1 that I really wanted to discuss. Okay, in 14.4, we're going to start talking about colors and the ideas of what colors come from. And from our visible spectrum, and this is something that I found interesting. Notice on your diagram here, what's missing? What's missing? What is it? Yeah, indigo. We always write Roy G. Biv. Indigo is that color between blue and violet. So if you remember looking at like the rainbow and the colors, indigo really wasn't like its own color. It was kind of like a mix of the blue and the violet, right? It wasn't blue, but it wasn't violet, so we had this other name, indigo. But in your textbook, they don't use indigo. And what Elliot was mentioning was that if you do a little bit of research and read about it, Roy G. Biv sounded better than Roy G. Biv. Like they added the I there for Biv, and indigo happened to be between them. But as one of the colors in the spectrum, you don't really consider indigo there, because it's a combination of the blue and the violet. I never read that anywhere, but I could see that in the diagram in your text.
So like, it doesn't have anything to do with proportions now, because like before you mentioned that last part, I assumed that like maybe like the bluer and the colder range was maybe like longer or something.
Well, the wavelength or the frequency is what's determining it. So it's a longer or shorter wavelength for sure. But when it comes to these colors here, you're looking at the difference in wavelengths. The combination of these colors create other things. And that's where you're thinking of like where you add pigments together to get a third color. But here, when it comes to these colors, these are just different wavelengths that you're seeing. Now, why is only green coming off here? Why do you only see G coming off of here?
The cells in the plant.
I don't even mean that. I mean just physics-wise, not even bio-wise. Why do you only see... What color is a leaf?
Green.
Green. So what do you see again? You see the reflected color, right? So when you see this purple iPad case, you're seeing purple or violet come off of there. You're seeing that wavelength. The material is trapping all the other wavelengths and only reflecting specific wavelengths off.
Which is why black clothing gets really hot in sunlight.
Yeah, why? Explain that, because we're going to talk about that.
All the wavelengths.
Yeah, black is the absorption. You should jot this down if you don't know this. Black is the absorption of all the wavelengths. What is the color white?
The reflection.
The reflection of all the wavelengths. So in the summertime, When you wear a black shirt, you notice it gets really hot pretty soon, right? If you wear a white t-shirt, it doesn't heat up as much. Ever play basketball in the summertime on like a blacktop? It's the worst. When I was a kid, we used to always play in the street. We play street ball in the front, so I know, who would have thought? The surface was just black asphalt. You know, you like pave your driveway, it's black asphalt, it gets really crazy hot. It's like when they pour tar down, and it's just that black, like thick tar. Well, in the summertime, my dad at one point decided we used to have tenants in our back. So we had two driveways, one in the back, one in the front, because the tenants used the back driveway. But eventually we stopped renting part of our house when I had 3 brothers. So we decided, let's make that into a basketball court. So we had a basketball court in our backyard. We just painted lines on it and stuff. But in the summertime, it was terrible because we'd always play barefoot. We just liked to play basketball barefoot, and it was a smooth, like asphalt surface, so we didn't cut our feet much. But it was just convenient in the summer because we had a pool, so we'd run from the pool to the, play basketball, go in the pool, play basketball in the pool, whatever. But the idea was the black asphalt would absorb all of the light. So what do you think would happen? It would get really crazy hot. So you would see, the actual heat waves coming off the asphalt. So we would have to go with a hose and hose down the asphalt 2 or 3 times to cool it off and then play. But within a half an hour, it would all evaporate and it would heat up again. And you'd have to do it again over and over. But it was one of those things where we were like, oh, we wish we had used concrete instead. Because concrete is like a gray color, right? You ever look at concrete, actual concrete? It's like a gray and reflects a little bit more light. Asphalt is black, so it would always heat up. So afterward we realized, oh, it would have been better.
Were you already aware that
I mean, yeah, it made sense, right? That black would always heat up, so what was the reason? It was absorbing all that light or that energy, whereas the color white would reflect it.
Play shirt and skin.
No, it's me and my 4 brothers. 3 brothers. That's awkward. Next. Let's take a look at the primary colors again. Again, these are not the primary pigments. These are not the primary pigments to be confused with in art. Okay, the primary colors we're looking at here. And where have you seen these 3 on the outside, red, green, and blue? Where have you seen these 3 primary colors before? James? Displays. What do you mean, James?
They use a combination of red, green, and blue pixels to create all of them.
Absolutely right. So a TV, a monitor, any display, James uses the word display to be generic, but any sort of monitor uses the combination of red, green, and blue light to display the pixels in those colors. Every pixel you see is a combination of those levels of red, green, and blue. So when you look at your menu and you go to your contrast and all your settings and the video settings, you'll see the different color settings, especially old TVs. Old cathode ray tube TVs, the big ones that have the actual projection onto the TV, old school ones, the glass front, those a lot of the time, after a long time, the alignment would be off. And you would see like a green shadow under certain things. And that was because the 3 colors were not aligned properly. You'd have to sometimes change. And you would have to get somebody to come in and fix it. And they would realign it for you and charge you out the wazoo just to fix the TV. You never heard that, out the wazoo?
I can just not imagine as a kid.
Instead of saying that curse word?
I can just imagine you imagine making sure that he does glasses and the beard.
In reading glasses? So, you're probably thinking of polarization too. What do you mean by reading glasses? Give me more.
No, I said 3D glasses.
Oh, 3D glasses, absolutely. I think it said reading glasses. I'm like, I don't think they're in reading glasses. 3D glasses, right? That's a really good one. I didn't even think about that. 3D glasses is just a combination of these colors again. Absolutely.
3D glasses are only red and blue.
Say again?
3D glasses are only red and blue.
One is red and one is blue, right?
Yeah, but I mean the same concept.
The concept is the overlapping of the 2 different colors. Your eyes are interpreting it. What do they use now? They're just clear, right?
Yeah.
It's probably because they can polarize and change the light without actually doing that. Another one that's interesting is in your eyes. In your eyes, you have certain things
Rods and cones.
that allow you to interpret color, like cones and rods and things, right? And those colors are interpreted by these 3 major colors: green, blue, and red. So the cones are the receptors in your eyes that could see those 3 visible light colors. And they are then combined in proportion to come up with the color that is actually showing you. James.
That's why if you have like a disco colors on it and you spin it fast enough, it appears white.
Yeah.
Because the cones can't keep up with the change.
That's really cool. I never thought about that analogy, but James is right. We're going to see in the video, we're going to see that combination shows up white. But James is saying if you have the color wheel with these three colors and you spin it fast enough, you see white actually there because you're seeing the combination of those three colors.
Yeah, but what if
Okay?
you move your try, like if you try and move your eyes while it's spinning?
You just get a headache. I mean, it's like, have you ever seen, you ever look at a car, when a car's tires are spinning fast enough, it looks like the tires are going backwards in rotation?
Yeah.
The reason is that your eyes can't keep up with the oscillations that fast, so you're lagging behind a little bit, and that little lag is causing your eyes to see a little bit behind every time, and it makes it look like it's going backwards.
That gets me excited.
So the overlap of green,
He works out.
red, and blue is actually white light. That's what you're seeing in the middle. Okay, the transmission. And in a minute we'll show a video that will clear this up a little bit. Let's finish with the last polarization before we take a look at that video. So here's what polarization is, and I'm going to give you the simple version of polarized light. Okay, there's a lot more to it than this. And those of you who has polarized glasses or sunglasses, okay, this is explaining what it's doing here. Let me give you a quick analysis. So, non-polarized light, or we call it unpolarized light, has oscillating electric and magnetic fields that are not aligned. So for example, take a look at my hands, okay? Remember EM wave, if it travels this way, the magnetic field acts this way, the electric field acts this way, and they were always transverse, remember, perpendicular, and then the actual beam went that way. Well, what's happening here in this one is that one beam looks like this. Another beam looks like this. Another beam looks like this. They're all at angles, okay? But polarized light takes those magnetic and electric fields and magnetizes them on the sides, which lines them up. So take a look now, and you can look carefully on your diagram. All of these vertical yellow arrows are representing the oscillating electric fields. See the vertical arrows up and down that are yellow? And notice that they're all like this now. They're all aligned, even the different beams. So you went from beams that were all at different angles and pitches to all these beams that are all at the exact same angle with their magnetic and electric fields. And what this does is it actually reduces the amount of glare as a result. Which is why if you ever, in even the summer, or it could be the winter, if you've ever walked around, I say summer because you really do with sunglasses. With sunglasses that are polarized, look at windshields next time you're wearing polarized sunglasses.
Okay.
As you're walking through the city, just take a notice, you'll see. Look at a windshield that's reflecting light. You're going to see some crazy stuff. You're going to see like the different colors of the spectrum come on there because they're both polarized. Okay, a lot of windshields are now polarized.
And in the Arctic, the glare from the ice.
Yeah, so either on snow or people that sail. Sailors a lot of the time wear polarized sunglasses because it reduces the glare of the water. Okay, at night when you drive, the glare is magnified a lot at night. So when you're driving at night, if you wear prescription, you should make sure you have them on. So even like I only started wearing these recently because I've been getting headaches. But last year, I've had them for 2 years, and last year I was still driving down when I was in DC. And when I came here, I got rid of my car because of the subway, but I was still driving, and at night when I would drive, I had to wear these glasses, or else it was unbelievable. The glare that I would get from oncoming traffic driving at night, like especially on like I-95 or the turnpikes and stuff, because there's 4 lanes of cars on the other side, it was an amazing glare, like to the point where it really hurt my eyes. And then I started wearing glasses, and they're polarized glasses, it reduced all that glare.
Yeah, I saw this really dumb commercial on TV of these people who were like, I can't see when I drive at night, so I'm gonna wear these sunglasses.
It helps though with regular glasses. I don't know if I wear
Yeah,
sunglasses.
like yellow, so.
You have to.
Where's the dudes were
Look where
yellow?
sunglasses
There
are.
are yellow people.
No, the left.
Let's hear another comment.
If you take like polarized sunglasses or something, like one like vertically like that and the other one like that, don't you like not see?
Yeah, that has to do with blocking each other. So if the polarized waves are at perpendicular angles, you can't actually see through them. And Mike Tierney sent me an example of this video where a person takes off part of the front of a laptop screen and then wears polarized glasses, but because there was a polarized screen in front, unless you're wearing the glasses, you couldn't see the screen. So for example, the light you see from the screen was coming through a polarized piece of glass. When they removed that polarized piece of glass from the laptop just looked white, completely white, because the screen was not transmitting it. But if you had polarized glasses and you went like this, you could see those spots on the screen, like as if it was like letting the light through. Everything was white except for those spots. So I'll take a look. I'll put it on newsfeed so you can see the video of what I'm talking about. I don't know where it is, but let's take a quick look at the combination of light colors now to see what happens with transmitted light. Okay, it's just a little video.
Mr. Howell, wait.